Hello, everyone. Thank you for sticking it out to the end of another long and wonderful day at ONA. My name is Dan Ratner. I'm going to be talking to you with us about machine learning today, and I'm in the unenviable position of being between you and the Dirty Sixth and Austin's amazing food and music scene. I realize that this is a real challenge, and so I'll try to keep my at least initial remarks reasonably brief. But what we're going to be talking about today is, I think, not only one of the most exciting trends in technology from the last couple of years, but really one of the most exciting trends I've seen in my own 2 decades as a technology executive and entrepreneur. And it's one that I think really has the opportunity to be impactful on almost every industry, and certainly not least of which is on journalism. So I hope it's worth missing the first round of drinks for, and I look forward to chatting with all of you during the cocktail hours that are to follow. So who am I and why am I up here? Because I'm also the co-founder and CEO of Public Good. And what we do at Public Good is make news actionable by inserting our technology into the templates of major publisher websites to allow people to immediately take action on the news. So for example, if you're reading the coverage about Hurricane Florence and you want to know how to help storm victims, we would have a card or a chat bot in that piece of content that will say, here are the organizations that are working on this on the ground, here's how you can donate, here's how you can volunteer, here's how you can spread the word. That isn't a new idea. We've had Red Cross banners on websites for a decade or more. But what really makes Public Good's technology unique is that we made it scalable through the power of machine learning. So we developed systems that are able to determine what a piece of content is about at publication time, figure out what issues are being raised in that, and find other information which is relevant, like where the story takes place, or who the reader is, or any entities or organizations that might be mentioned in that piece of content, and be able to use those to create personalized real-time experiences for people that will enable them to take action. It's just one example of sort of content augmentation or a user engagement tool which is based in machine learning. But it's really led us down this journey of really examining machine learning as rigorously as we can to understand these systems and realizing a lot of the challenges that happen when you start trying to operationalize that technology and use it in the real world and often really kind of dirty world of news content. So that's why I'm up here and why I'm interested in this topic. But I think that having had a number of conversations and sat at some of the tables downstairs in some of the previous sessions, I think one of the things that's super helpful is to start by putting kind of a box or a definition around kind of what we're talking about when we say machine learning. And I think in the session yesterday that Knight hosted, which I thought was wonderful, they mentioned that the goalposts for machine learning continue to move, and I think that's emphatically true. But this is a pretty good, fairly stable definition that I personally find really helpful, which is machine learning is pretty much just any computer system that gets better at its job by the accumulation of data rather than by the addition of code written by human engineers. And that is a powerful idea, but it's not necessarily a new one. It really goes back to the 1950s and 60s with computer science's pioneer and codebreaker, Alan Turing, who had this idea of what happens if we had a machine that learns from experience that could make progress that was not foreseen when the original instructions were put in. But as with so many visionary ideas, about half a century passed without that being the norm for how we develop software. So almost all the tools that you use on a day-to-day basis, whether it's a word processor or a spreadsheet or web browser or anything else, are in fact developed by teams of human engineers who sit with product designers and figure out what problem it is that they want to solve and how best that could be done, and what happens when you click here, and what happens when you move the slider, and how these different interactions should really take place. When they want to add features, those same engineers sit down, they develop the features, they develop the capabilities, too often they develop new defects, and then they push them out either transparently into their websites, or they nag you ceaselessly through your Apple update screens about why you should put the newest version in right now. That isn't to say there was no progress until recently in the area of machine learning. And I think it's really helpful to kind of cast our eyes back a little bit and talk about one area that I think has really impacted probably everybody at ONA over the last decade that is a characterization of machine learning that I think has some really important lessons for us today. And that area is recommendation engines. So just a question, how many of you have a website or a property which uses some kind of automated recommendation tool to suggest additional content to users? Almost everybody. And if you don't have it yourself, then you're almost certainly plugged into Taboola or a social network or to another content recommendation framework that does use these kinds of techniques. And so I think it's really useful to maybe dig beneath the surface a little bit and understand a bit more about how they work. That's sort of my goal today for this session, by the way, is I'm not going to talk a lot about products, because I think we're really in the early days of products. I'm going to talk a lot more about how these things work and try to give enough of a framework to be able to analyze products and kind of think about these things and know where to ask questions and know where to poke holes and kind of know what to be worried about and what not to. But I'm happy to talk about individual products when we get to Q&A. So let's talk about these recommendation engines. Let's kind of discuss a really simple one. In the early days of recommendation engines, we mostly used a technique called a collaborative filter. So the basic idea is if you are, say, Netflix, and you know that 76% of your viewers who are watching Mad Men and Breaking Bad also enjoy West Wing, you can feel pretty confident that recommending West Wing to your other Mad Men and Breaking Bad viewers, well, you're going to be right 76% of the time by definition. It's a really simple, really useful technique. And when you add just one more dimension to that data, you do some good old-fashioned marketing segmentation. And you say, does this look the same if my users are, say, New York and San Francisco? Does this look the same for my urban users or my rural users? Then you get what Facebook cleverly branded behavioral targeting, and you can add a whole new dimension to this and a whole new level of accuracy. It's actually really not that hard to do if you have a reasonable amount of data about how users interact with all different kinds of content. This isn't something which is as data hungry as some other systems are, but it was a big enough field that, at least until relatively recently, was mostly done offline, and those were sort of pre-cached and gotten ready for somebody who would visit a site. Now we're at the point where we can actually make these recommendations in real time. The math behind this is also not new. Mostly we use a technique called statistical regression, which goes back to the early 19th century. Folks like Legendre and Gauss, the one dust your old textbooks off. And it's a matter of using a lot more data and doing it a lot more quickly and adding some of these refinements in order to make recommendations. But almost all of these systems have two kind of major characteristics in common. So one of them is you get what you optimize for. And so if you optimize for clicks, you will tend to get more fiery clickbaity headlines. If you optimize for, say, article completions, you will tend to get more of your best content surface, but maybe with the expensive traffic. And so almost all of them under the hood actually use some kind of algorithm to determine the trade-offs between the different variables that you might want to be optimizing for. So whenever anybody is showing you a recommendation engine or demonstrating one, it's super important to know what it is optimizing for and what the effects of that are going to be. A second really common attribute of all recommendation engines is that over time, those recommendations converge. Or another way of putting it would be ossify. You know, you've got these shows, Mad Men, Breaking Bad, West Wing, none of those are new. But since I've been recommending them for years, I'm going to keep recommending them because they tend to get good results. So it makes it really difficult for a new show or a new piece of content to be able to break into that mix. If you put both of those trends together and say, okay, I'm going to keep recommending the same things, and I'm going to optimize for something that I'm not necessarily clear on what I'm optimizing for, I'm kind of looking for a short-term hit, then you get the underpinnings for, of course, what we're now calling filter bubbles. And I'm not going to say that recommendation engines are exclusively responsible for filter bubbles, but what they do is exacerbate our underlying human psychology, our confirmation bias, the other things that make us really want to see content that supports the things that we already believe. And if you're lazy about how you construct these things, they are doing the job you asked them to do. They are creating those recommendations. They're getting people to do the things that you wanted, more clicks, more likes, more shares, more whatever, but possibly with this other side effect. And again, they're really effective. I mean, you can see that from a point of view of just the growth of social media as a primary source for people to get their news. But you can also see the side effects in a graph like this, which you may have seen before, which is just a graph of Twitter likes and shares. And you start to see that this goes beyond a simple like or a simple share. And even though Twitter did not have any idea when it was deciding what should appear in your newsfeed or what your political affiliation was, nevertheless, it appears in the pattern of usage because it continues to reinforce those biases. So as we start looking at other trends in machine learning, we see these same things. You know, get more of what you optimize for, and be really careful around these things. Machine intelligence is intelligent, but it is not wise. So we need to give it a lot of guidance. But that is not the problem that I think has really gotten people very excited. As I said, statistical regression is a technique that's been around since the 19th century. Sure, we do it better, we do it faster, we do it cheaper. But what is it that we're doing which is really transformative, that is getting people really excited about AI and saying AI is going to change everything? I think one example of that is handwriting recognition. I am not for a moment suggesting that I'm going to do a straw poll here and ask how many of you still submit reports to your newsroom by hand. I'm not talking about recognition from a practical sense, but more just as a problem to be solved. Handwriting is almost impossible problem in traditional software engineering, which is why for so many years we've really struggled with this kind of an interface. Everybody has characteristics to how you write. You have different swoops and curls, and some people write in cursive, and some people write in uppercase or lowercase or mixed case. I cross my sevens. My twin 6-year-old boys like to draw my walls with markers that they hold in a fist grip, which I can recognize but not necessarily appreciate. But all these things become really hard. It's really hard to construct a set of software rules for being able to recognize this. It's also really hard to use a technique like regression for being able to analyze it. There are just too many variables, even if you could characterize all of them. So it requires an even bigger departure and starting to think about things in a really different way. And in this case, it required somebody like Geoffrey Hinton, who's a professor of computer science at the University of Toronto, to say the brain's got to work somehow, and it sure as hell doesn't work by somebody writing programs and sticking them in there. And so he, along with a few contemporaries, also found another old idea that was ready for another look, which was called neural networks, and tried to apply them to this problem. So out of curiosity, how many folks out here kind of have a basic understanding of how neural networks work? Okay, cool. So it is an oversimplification, and it's a little bit of a misnomer, but the original idea was to be able to say, well, how can we solve problems in more or less the same way a brain does? Well, why don't we try to maybe a computational model of a nerve, and ultimately kind of a computational model of the brain, and see whether or not we can solve some interesting problems that way. But that's also really computationally difficult. You end up having to train these systems on a huge amount of data, and you need an awful lot of these simulated neurons and simulated interconnections in order for it to work. What Hinton has really kind of realized, among others, is that two major trends in computer science and kind of in the world around us were converging to make that really possible. The first one was basically infinite, cheap cloud storage. You can keep as much data as you want, it's there on demand, it's available for your algorithm, and you can rent machines as you need them. The second is that chips that are really good at being able to simulate neurons that were originally developed for computer gaming, they're called GPUs, were also becoming really cost effective and really easy to deploy. So being able to run a problem like handwriting recognition even on a home PC was a really realistic thing to be able to do. And that really got a lot of companies that had been collecting a lot of data, partly for recommendation engines and partly for other purposes, to say, oh, wait, we've got this huge trove of data. We've now got this additional tool set and a whole different way of looking at these things. What can we do with this data, kind of given all of these new techniques? And I think another thing that's kind of important to think about with a neural network is they are really data hungry. If you want to train a neural network to do almost anything, the way that you do it is by setting up what is actually usually an off-the-shelf piece of software. You can just go to Google and download TensorFlow. But then you end up having to feed it a massive amount of data because it learns almost entirely by example. So let's say we wanted to teach a neural network that what it wanted to do was to recognize American flags. You can't say to your neural network, hey, look for boxes with 13 stripes and 50 stars, and those are American flags. And here's some examples, and you can go learn from those. What you need to do is to show it millions and millions and millions of images of everything from American flags to Volvos, and tell it this is an American flag, this is not an American flag, this is American flag, this is something different. To give you an example, at Public Good, we end up needing somewhere between 50 and 100,000 articles classified for any given category in order to be able to train our systems. It's a lot because you can't kind of give it any obvious examples, whereas if I was trying to train a human, anyone in this room to be able to do it would probably do it with a dozen. So needing all of that data is a big deal, and that tends to reinforce in the artificial intelligence and machine learning world sort of the tech oligarchies, the companies that have that data. But it will also, I think, reinforce here in our own news industry, folks that actually have sufficient presence to be able to have your own destination websites that people actually visit, and also should kind of increase the costs of how you think about having your content syndicated to places where you cannot get that user data, because you will not have that available to be able to feed the systems to the degree that it's not that to be valuable for you. So it's another rent that is extracted by almost any of the networks that are redistributing your content. But another thing about these networks is because of the way that they're built, feeding them these examples, at least until recently, we didn't think much about how they worked. We were kind of satisfied that they work really, really well. You can feed it all these images and ultimately becomes, kind of air quotes, better than a human in being able to make a determination like this is an American flag. Until the first time that it tells you that a French flag is an American flag, you think, hold on. You've been completely right 99.999% of the time. How could you make a mistake like this? It doesn't look anything like an American flag. And then you realize that what the algorithm was doing was not looking for stars and stripes, it was looking for red, white, and blue. And as we started unpacking these algorithms, and this is a really rapidly developing area in machine learning right now, is to look into these algorithms and try to understand how they work. I think we both get some more insight into how our own brains work, but aside from that, we start finding these little tricks that turn out to be really interesting and potentially useful. Like this image of a stop sign, which was modified with a little bit of graffiti by a research group, fooled a prototype autonomous car into thinking that's not a stop sign, that's a 45-mile-an-hour speed limit sign. And you can just imagine what kind of havoc could be had in your neighborhood with some folks kind of going around and putting some tape on stop signs. Not everything has potentially fatal results, but that is a case where that's definitely something that makes you want to stop and think. But it's also not totally negative. You can think about something like an adversarial image as being a way of doing an attack. But like almost everything in machine learning, it actually is a double-edged sword. It can be used for this kind of hostile thing, or it can be used for things that can actually be productive. And a good example of that is now using neural networks and using machine learning not for analysis, but for generation. I'm sure that in some of the sessions you've heard folks talk about natural language generation, about being able to create content on demand, about some of these other ideas. A lot of this is powered by what I think is one of the coolest ideas out there, which is called a generative adversarial network, or a GAN. It's not worth getting into a lot of the details, but a really simple way of thinking about a GAN is almost like you've got a crime scene sketch artist on one side, and you've got a witness on the other, and the crime scene sketch artist just keeps coming up with images of a possible suspect until the witness says, yeah, that one. And then that's the one you publish because you're probably pretty close to accurate. What you've actually got is two AIs essentially working against each other. One is generating images, the other is scoring those images and saying, yeah, that's right, or that's wrong, that's right, or that's wrong. And it lets you go through a massive number of iterations relatively quickly with results that are really compelling, like the bird image at the bottom, which is from a project called Attention GAN, where you just put in a sentence, and it's actually able to generate an image which looks pretty compelling and pretty realistic. It kind of mimics that sentence. This is useful for a variety of different techniques, and it's especially useful if you want things to start to look really natural. But it also should kind of give us a little bit of pause, because what it means is that you are going to be in a perpetual arms race of AIs between those that generate and those that identify. So anybody that says, okay, well, we're going to go out and we're going to track down all of the fake or dubious content using an AI system should remember that the fakes are being trained against those systems, and that that is an endless arms race back and forth. So to the degree that our forensic systems continue to develop more rapidly than some of our faking systems, you should definitely not assume that those are in the hands of most individuals. So we would all like to think that, especially in this kind of world of potentially fake information, that we would be able to rely on computer systems to help us, and we probably will. But they're not necessarily going to be completely reliable, even though they are getting increasingly more sophisticated. In fact, we're going to be relying a lot on context and on provenance and on good old-fashioned reporting, but it's a case where even skepticism doesn't necessarily get you what you want. So this actually comes from a recent report by Robert Chesney and Danielle Citron. Robert Chesney's a professor here at the University of Texas, and Danielle Citron's at the University of Maryland. And they've coined this new term called the liar's dividend. They say if we allow fake content to make us too skeptical, then in fact what that can do is bury real content that just happens to be sensational. So if you end up having, for example, a videotape emerge of a presidential candidate bragging about having sexually assaulted a number of women, and he says, fake news, fake news, fake news, you have to accept that it just might be because it could be. But actually that turns out to be real. So we don't want to get to a point where we start dismissing things just because they're sensational on the grounds that they might possibly be fake. So this whole thing that I've kind of walked into here about fake content, deepfakes, and these other kinds of things, also illustrate another area in machine learning, which is a major trend as well, which is it's being consumerized. So the ability to create a fake video is not new. I mean, all you had to do is go to the movie theater to see that. Hollywood special effects studios have been doing this stuff for decades. What's different is that you can now download something like Fake App. If any of you actually tried this out, downloaded it, and put it on your machine, it's probably good because most of the current versions of fake apps also have Bitcoin mining in the background, so you probably can kiss your computer performance goodbye. But the fact is that you can download these apps, which are more or less consumer friendly. They require you to watch a 10-minute YouTube video. In my case, it took me about a night of installing device drivers and kind of swearing at it, but no actual writing of code, in order to be able to superimpose a video of the 45th President of the United States over a video of Nixon resigning. Sorry, I used to work for Obama. But my fake isn't going to fool anybody, but it shows how easy this is to do. There were a little ticks and blurs and things like that, but those will get ironed out over time. There is some kind of generative adversarial networks and other techniques that I described. So it's not really sufficient to trust AIs to police other AIs. We are definitely going to have to look to other techniques. I'll talk about at least one of those kind of as I wrap up here. So with these computers becoming more powerful and these techniques becoming more powerful, I think it's always good to get a little bit of perspective. I do this one definitely a little bit tongue-in-cheek, but one way to think about how smart these AI systems are is how we think about how intelligent we are compared to other animals, which is kind of how many neurons do we have? How many neurons do they have? Well, state-of-the-art NVIDIA processor can simulate about 2 million neurons in real time. That puts it a little bit ahead of a cockroach, a little bit behind a frog. And so it kind of depends how confident you want to be in the ability of a cockroach or frog to figure things out. But before we get too excited about our 86 billion neurons and think about ourselves as too superior, it's also worth remembering that most of our neurons are used for things like digesting food, or storing memories, or processing visual information, or breathing. But relatively little of them are actually used for an immediate conscious task. Computers don't get bored. They can have problems really narrowly defined. They have essentially infinite and perfect recall of information. And you can create all sorts of optimizations if you're trying to solve a special purpose problem. So for certain kinds of things, computers are extremely smart. For certain kinds of things, they're extremely dumb. It requires us to be able to exercise a very large degree of judgment, to kind of know which of those things is applicable for any given problem that we're looking at. So I said I would give us at least one hook into another place where we might look for technology to help us out in the world of deepfakes and fake information, as I'm kind of wrapping up here. And at least one idea is to do what art dealers have done and say it's not enough just to look at a piece of art to understand whether or not it's real. We have a lot of techniques, and some of them are very sophisticated. You can do carbon dating, you can do X-ray fluorescence, you can do all sorts of other things. You can just look at the technique of the artist. But ultimately, the thing that is the gold standard is to have provenance, is to be able to trace that individual piece of art all the way back, ideally to the hands of the original artist who created it. That's not something that we traditionally do with digital content. It's something which is starting to be done. There are apps that you can do that will now location stamp any photos that you take, and also hash those photos so that you can prove that they were taken in a specific time in a specific place. We're starting to see some of those things fall into place. But even after publication, what can we do that will prevent our content being modified? Well, we'll prevent our images being modified and being reused and synced, or maybe something that we did. It might perhaps be useful to have some kind of an open ledger, some kind of a system that you could check those into, where that could be cryptographically verified, where we could get some kind of trust around all those things, and that we could all participate in and all see in some kind of a useful way. I've kind of given a roundabout description of what at least one implementation of this is called blockchain, and that's something that I think will be discussed more in kind of side by side with AI. It uses a lot of the same techniques, it uses a lot of the same hardware, it uses a lot of the same ideas. So maybe we'll get an opportunity to discuss that next time, maybe in 2019 in New Orleans at ONA. So with that, I really just wanted to open it up to questions and conversation and anything that anybody would like to talk about in machine learning and in journalism, any of the products that you've seen, and anything you'd like to discuss.